Hey, welcome back, everyone. Hope you enjoyed this short break. We are the Oceanic Exploration Cruise Company, and we are here today to present to you the design for our new expedition vessel, the MV Polar Puffin. No clicker. All right. To begin, I'll start with an outline of what will be covered in this presentation. We will start with an introduction of the team members and acknowledgement of our faculty and industry mentors. Then I'll cover the vessel objectives and mission requirements, as well as discuss the vessel systems. Max will then continue the presentation. Right, there's some trouble with the clicker here. Max will then continue the presentation and discuss the propulsion and electrical systems, as well as the vessel hull form, anticipated loads, and structural arrangement. Rebecca will then continue with an overview of the general arrangement, as well as discuss the vessel's 3D render. Caleb will then conclude the presentation with a summary of weights and centers, vessel stability, and the rules and regulations referenced. We will then take questions from the audience. All right. First off, our first group member is Caleb Reckenfelder from Wisconsin. Caleb's most recent winter work experience was as an engineering intern at Bay Engineering. Our second group member is Rebecca Carson from Maine. Rebecca's most recent work experience was an engineering intern for Stolt Tankers in the Netherlands. My name is Steven Katz. I'm from New York, and my most recent work experience was as an engineering intern at General Dynamics Electric Boat. Lastly, we have Max Rothschild from New Jersey. Max's most recent experience was as an engineering intern for the American Bureau of Shipping. At this point, I will take the time to acknowledge our mentors who assisted us throughout the design process. I am terribly sorry if I mispronounced someone's name. First, we have our professors, Prof. Golden and Prof. Boyd, and our industry mentors, Will Calley, Jevin Chan, Hampton Dixon, Aswin Janardhanan, Ben Leons, Ed Mokler, Don Rickerson, and Roy Serafian. Thank you all for your assistance. The objectives and requirements for our vessel were laid out for us at the beginning of the project by our client, Prof. Golden. As can be seen above, the Polar Puffin is intended for operation in both Arctic and tropical climates. This wide range of cruise destinations changes with the season to keep the vessel active all year round. Cruises are expected to last up to 30 days and cover up to 5,000 nautical miles. As per the client's mission requirements, our ship is capable of launching and recovering 10 rigid inflatable boats, as well as one submersible large enough for 9 passengers. This provides our passengers with an opportunity to leave the ship and explore the destinations of the cruise. The passenger decks were designed with comfort in mind for a luxurious cruising experience. The ship is fitted with gyroscopic roll stabilizer to assist in passenger comfort. The ship is capable of operating without fossil fuel emissions and with a range of 5,000 nautical miles as per the mission requirements. To meet the range and emissions requirements, a 10 megawatt nuclear electric power plant was selected to power the ship. Nuclear power generates zero emissions and has high energy density. We were permitted to ignore port regulations related to nuclear power, as this is a concept vessel and will not actually be constructed in the foreseeable future. In addition to emissions and operating range, this allowed us to easily meet the high hotel loads of a luxury passenger ship and the high power requirements for ice breaking. The Polar Puffin has a BV Class 7 ice breaking capabilities. The vessel has an approximate length of 120.5 meters, beam of 20 meters, draft of 4.9 meters, and has a total capacity of 270 individuals. As set by the client, the ship has a design speed of 15 knots, a service speed of 12 knots, and an ice breaking speed of 3 knots in 0.6 meter thick ice. Here, we have the list of major systems of our vessel that were considered in the design process. Each system and their effects on the other systems has been addressed in their design. For this iteration of the design spiral, we did preliminary design work on the structure, powering, auxiliaries, mission systems, and tankage. First off, I'm going to talk about a little bit about the cooling system. This diagram shows the ship's cooling system. It utilizes fresh water from a header tank to prevent corrosion and operates in a closed loop to reduce the load on the freshwater generators. 3 centrifugal pumps were selected in a parallel configuration to supply fresh water to a main supply manifold, where it is then split by pipe diameter and throttling valves to ensure each branch gets the amount of water required to reject their heat load. The vast majority of the cooling load is from the ship's nuclear reactors, which each generate 15 megawatts of heat, meaning 10 megawatts of which needs to be rejected. The secondary cooling loads in total contribute 1.2 megawatts of thermal load to the system, significantly less than the 20 megawatts total from the reactors. From left to right, the secondary loops consist of the HVAC, refrigeration, and auxiliary machinery. Each secondary loop takes cooling water from the supply manifold. The components in each secondary loop are connected in parallel. The outlet water for each loop passes through a throttling valve to equalize the pressure before all the loop outlets flow into a common return manifold. The common return manifold then flows into two shell and tube type heat exchangers in parallel, where the heat taken in by the fresh water is rejected to the ocean. Afterwards, the water flows back to the header tank to go back through the loop. I will now pass the presentation off to my colleague Max, who will discuss additional vessel systems.
Thank you, Stephen. I will now talk about the propulsion and electrical systems. This ship has a nuclear electrical arrangement. This type of arrangement is very similar to a steam turbine or electric drive system. The ship has two nuclear reactors, each providing 5 megawatts electric and 10 megawatts thermal power. This provides plenty of power for the ship's services and hotel loads. The thrusters being used are two 1.6 megawatt as-pod thrusters, which are certified to work in Arctic and Antarctic conditions. An additional transverse thruster was placed in the bow to assist in maneuvering in docking and ice flow conditions. The emergency diesel generator is sized to supply power for all emergency systems on board the vessel. Figure 9 is the ship's one-line diagram. The power generation and main propulsion are on the 4,320 volt system, and the propulsion uses 3,216 kilowatts. The auxiliary machinery and HVAC units use 480 volts and consume 1,542 kilowatts. The galley appliances and Zodiac launching equipment run off of the 240 volt system and take 325 kilowatts. The final piece is the 120 volt system, which supplies power to all smaller hotel loads, lighting systems, and other spaces. This consumes 91 kilowatts. The whole system is wired in a three-phase delta configuration. This is the 4,320 volt section of the one-line diagram. Here you can see the ship's service turbines, which are powered by the nuclear reactor. Next, you can see the emergency diesel generator, which can be connected to the full ship's grid. The emergency generator was sized to provide 1,240 kilowatts, which is enough to power the emergency systems. The final parts at this voltage are the main propulsors and bow thrusters. These are at such a high voltage in order to carry enough power to the as-pods and to minimize transmission losses to the bow thruster. The 480 volt section is the first in our two medium voltage stages. The items that require power at this voltage are auxiliary machinery, HVAC systems, and the Trident submersibles charging. The emergency generation was stepped down to this voltage to supply power to essential pumps and machinery as dewatering and firefighting equipment. This is the second stage medium voltage, which is at 240 volts. This voltage is used to power large galley appliances such as stoves and ovens, as well as other smaller motors such as the overhead crane, which is used for launching the Zodiacs. In figure 14, the 120 volt emergency panel can be seen, which provides power to smaller firefighting equipment and the ship's hospital. This is the final section of the one-line diagram, which contains all of the main 120 volt loads. These loads vary significantly. Some of the loads at this voltage are small beverage refrigerators for the bar, electrical outlets for general use, and laundry services. I will now talk about the hull form. This is the body plan of our vessel. From this view, you can clearly see the inverted bow design to assist with ice breaking, as well as the flat transom, which is used to launch the Zodiacs and submersibles. Here you can see the shear plan. This view gives a good idea of the profile of the vessel, once again noticing the inverted bow and flat transom. The half-breadth plan is showing the water lines of the vessel. It can be clearly seen from this view. We have a sharp bow at less than 40 degrees to comply with Bureau Veritas's ice breaking regulations. Now we'll talk a bit about the anticipated loads. The first load which was analyzed was the hydrostatic load. This occurs because of the pressure of the water pushing in on the side shell of the ship. There are two environmental loads which were accounted for. The first is the impact of ice on the bow and side shell. The second was the wave loads on the ship. Both of these were accounted for using prescriptive BV rules. The final loads is the operational load, which is comprised of changing loads in the fluids tanks, the launching of the Zodiacs, and changing of food stores. Now we'll talk a bit about the structural arrangement. The reason for the larger size and closer spacing for the longitudinal stiffeners is that the vessel is ice-breaking class 7, which means it needs to withstand ice buildup as well as impact loads. The deck stiffeners were spaced and sized to comply with BV rules for global loads. In the next loop around the design spiral, local loading will be analyzed. The shell and bottom plating thicknesses were chosen to comply with Bureau Veritas rules for ice-breaking vessels. The deck thicknesses were chosen to optimize the section modulus of the midship. The girders are spaced to support global loads and tank loads. I'll now hand the presentation off to Rebecca.
Thank you, Max. I will now discuss our general arrangements. One of the first stages of our design was to create a general arrangement. This GA was adjusted with each step of our design process. This is the profile view of our ship along our center line. From this view, you can see a few main principal characteristics, including our X-shaped bow to meet our ice-breaking requirements, our glass dome observatory, our podded propulsion, and our aft hangar for the launch and recovery of our tender craft and submersibles. From this view, you can see our top 3 decks. The top 3 decks are entirely passenger spaces. This was chosen to allow a single cohesive recreational area for passenger entertainment and relaxation. Deck 6 holds the navigation equipment as it is the highest point of the ship. It is also an open deck that allows passengers a 360-degree view of surroundings. Deck 5 houses both an indoor and outdoor entertainment space, including a pool, jacuzzi, fire pit, and both an indoor and outdoor bar. This is to allow outdoor entertainment in both warm and cold climates. On deck 4, on the aft sun deck, you'll see 2 telescopes. This is for passengers to use and see wildlife, landscapes, and other faraway sights while underway. Also, on deck 4, we have an interior area that has a general entertainment spaces for passengers, including a gym, a sauna, a buffet, and a spa. At the bow of deck 4 and 5, you will see the interior of our dome observatory. The walls of this observatory are made out of glass as to allow panoramic views of the exterior from the comfort of the warm interior during cruises in Arctic climate. It will also allow the view of astronomical events at night, such as the aurora borealis, which are best seen in our main areas of operation. During the day, this space also doubles as a stage for performances. As it can be noted, the seating does not comply with our full passenger capacity. This is because there will be 2 performances of each performance, and we will stagger in passengers in order to minimize cluster. Lastly, forward of this space is an exterior viewing deck for passengers. It encompasses the full bow as to allow forward views of both port and starboard side. Next, you can see deck 2 and 3. Deck 2 and 3 contain mainly passenger cabins, with the addition of the bridge located at the bow of deck 3. The bridge is equipped with 2 enclosed bridge wings for extended view for navigation. Also, the captain and chief engineer cabins are located directly outside of the bridge to allow quick access in the case of an emergency. Also located on the aft end of deck 3 are the lifeboats. They extend below into deck 2, which is where the boarding location for them is located. This boarding location is located directly above the muster station in the case of an emergency evacuation. The muster station is located in the dining area, as the space has ample room for all passengers to gather at one time. From this view, you can see Deck 1 and Deck A. Deck 1 is the deck from which passengers board. Because of this, this is also the main dining and entertainment deck. It includes a shopping area, casino, and gallery. It also houses our two largest dining spaces, as it can be seen from these views, the aft being the normal dining space and the forward being an extra paid steakhouse. On Deck A, you can see is mainly a crew deck containing cabins, messes, and entertainment spaces for the crew. At the stern of this deck and extending below into Deck B is our stern launching station. This region is for the launch and recovery of our Zodiacs and our submersible, as per our mission requirements. Here, there is a hatch at the stern that opens to the water to allow the easy launch of these boats. The launch is assisted by a crane within the hatch to carry the boats in the submersible, as well as a slip dock extending out for the smooth launching of the boats with passengers on board. On Deck C, you can see this is our engine room and auxiliary spaces. It houses our two nuclear reactors. They are placed at midship due to their high weight and loading. Lastly, we have Deck D. This deck simply holds our holding tanks. It can be noted that there are no fuel tanks on our ships, as we do have a nuclear vessel. This allowed us to have additional spaces for passenger amenities. Here you'll see our simplified 3D rendering of our vessel. It was made to showcase the observatory dome and what it would look like, as well as the overall shape and appearance of the vessel in its operating conditions. I will now hand the presentation over to Caleb to discuss the weights and centers.
Thank you, Rebecca. To begin with weights, looking at table 1, I want to highlight the bolded hull structure on the top. The hull structure, coded under Swiss 100, contributes the most significantly to the overall weight at roughly 3,300 tons. It also dominates the longitudinal and vertical moments as well. Other major vessel contributors include the auxiliary systems at 740 tons, with a relatively high vertical moment of roughly 11,000 ton meters. This indicates that it's a considerable mass placed at a higher vertical position. Additionally, the departure and arrival loads at 828 and 1,024 tons respectively represent the consumable cargoes that shift slightly in vertical and longitudinal location over the course of the voyage. The propulsion and electrical plants are relatively light compared to the structural weight, but still contribute noticeably to the moment balances, particularly longitudinal, due to their location aft. Finally, we've included a service margin of 236 tons, which is a design reserve to account for uncertainties such as late-stage outfitting, future modifications, and this buffer ensures compliance with stability and trim requirements even as the vessel evolves. The total weight of roughly 6,000 tons for departure and arrival condition was summed. Here in Table 2, we can see a few standard stability characteristics. The 3 conditions outlined are light ship, full load departure, and full load arrival. The drafts for these conditions are 3.5, 4.7, and 4.5 meters respectively. And the trim for the same conditions are 0.4, 0.5, and 0.35 meters by the stern. These values generated through a stability analysis with GHS. The initial stability, we see that the metacentric height is relatively high at 4.4 meters. This translates to a steep initial slope on the GZ curve, indicating strong resistance to small angles. The vessel will resist rolling and return quickly to upright after minor disturbances. This isn't necessarily ideal for passenger comfort, which is something we wanted to look at in the next design. Looking at the righting arm, the curve reaches a maximum GZ of around 2.6 meters at 43 degrees of heel. It's a strong value that reflects good stability characteristics at a moderate heel angle. And the righting arm generally decreases after that and becomes 0 at approximately 88 degrees. The floatable length curve analysis shows that the vessel is compliant with single compartment damage scenarios, but it does not pass the 2-compartment flooding requirement. This will also need to be addressed in future. Here we can see these 2 cases. On the left, we have the single compartment damage condition. The curves here show that the permeability curves above the floatable length curve for all longitudinal locations, which indicates compliance with the subdivision regulations. However, on the right, we see the scenario for 2-compartment damage. In this case, the floatable length curve dipped below the permeability curves in multiple locations, especially midship. This means that if 2 compartments were breached, the vessel would not meet the stability requirement criteria. Here we evaluated the vessel's performance against the required minimum for all IMO intact stability parameters. Starting with the area under the GZ curve, we can see that in all 3 cases, the vessel exceeds the required minimums. For example, up to 40 degrees of heel, the required area is 0.09 meter radians, and all 3 conditions exceeded this. Again, the righting lever at 30 degrees is another benchmark with a minimum value of 0.2 meters. Here again, our vessel performs well, exceeding all values. When we look at the angle of maximum GZ, the minimum required is 25 degrees, and our actual values range from 32 to 43 degrees. The initial metacentric height is well above the 0.15 requirement as well. We found that a structural failure at frame 89, where the watertight bulkhead separates the engine room from other accommodation spaces, would lead to a flooding in both of these compartments. This condition would result in a significant loss of buoyancy and pose a major risk to the vessel. To address this, we propose 2 key design modifications. First would be adding a watertight bulkhead at midship to break up this flooded volume. And second would be adding internal subdivision within both of these spaces to eliminate the free communication of water. As shown in table 4, these changes dramatically reduce the draft increase from 11 meters down to 0.9 meters. This calculation is based on the lost buoyancy method using the formula shown, with an original waterplane area of 2140 square meters and a floodable volume of 1738 cubic meters. The reduced effective waterplane area after flooding brings a calculated sinkage of just under 1 meter. Finally, as guided by our client specifications, our ship was designed to meet the following national and international maritime regulatory requirements: Bureau Veritas NR 467, which is applicable for steel ships, and NR 527, which is specific for ships operating in polar regions. These codes were applied when designing the vessel's structure, machinery, and systems. Additionally, IMO's intact stability code for 2008 was referenced before shown. And lastly, the sections of CFR 46 that pertain to vessel, crew, and passenger safety were utilized to determine the required size of lifeboats, life paths, passive egress, and it was also used for firefighting equipment. I'd like to thank you for all attending. We will now field questions.
Will the ribs that you have in the aft compartment be using the same type of fuel as the EDG, or are there 2 separate tanks for that?
So the question was, do the ribs use the same type of fuel as the EDG? This was not analyzed within the project. However, they will both probably be using diesel. We're not sure of the exact type though. Thank you. Yes.
Thank you very much for the presentation. I had a question about the selected ice class for the vessel. So in the technical requirements, we talk about continuous speed of operation in 0.6 meters and thick ice, we're talking 150 millimeters of fresh snow. I understand with the PC7, its limit is 0.7 meters. So was there any further consideration of margin of error in those conditions? Because it might be difficult to determine that it's continuously operating at exactly 0.6 meters of ice. Thank you.
So the question was there a design margin added to the structure in order to accommodate more or thicker ice than the typical class 7? We For the ice breaking, we stuck to the 0.6 meter prescribed by the client and did not add a margin on top of it. However, in further iterations, that is definitely something that we should consider. Thank you. Any other questions?
I was wondering if you could comment on the arrangement challenges, the pod room and the hangar area for the aircraft.
So initially we had put our hangar area there with not enough room for our pods. So we had to go back and shorten the height of our hangar room later on in the design process when we added the acid pods to our GA.
Additionally, I think we added like a sort of stagger offset from like the normal deck height near the hangar compartment to give us more like flexibility for having enough space for the pods.
Were there any other considerations given for the launching of the ribs aside from stern launch?
So the question was if there were any other considerations given to launching of the ribs besides stern launch. At this time, there wasn't any other method that we chose to launch them. We do have the slip dock as well as the overhead crane, which can extend out and lower them into the water if needed.
We thought about doing it from one of the upper decks from the outside, but we thought that having a launching station would be better because we had the space for it due to having minimal fielding, having no fieldings.
And how do you envision embarking with ribs once they're in the water?
Passengers. So we have a slip dock there that has like a very not a very high ramp angle. So we would envision that the passengers get on the vessels first and then are lowered into the water.
I think can't find the slide. But I think there's also a mud room. So what like a transverse door would probably be adjacent to the mud room. Find it. Yeah, on the starboard side. To your question on the rib launching, I think one thing we were able to exclude right away was a moon pool because we were worried about ice and any like damage to the bottom of the vessel.
Any other questions? Yes, sir.
Earlier on, you mentioned the significant amount of waste heat due to the nuclear propulsion system. Was any consideration given to being able to reuse any of that waste heat for auxiliary systems such as water heat, partial water heating, or space heating, especially due to the polar climate that the vessel will be operating?
That's fun. So the question was there consideration given to other uses for the waste heat from the reactors besides just rejecting it into the cooling system? No, we did not consider it yet. Yes, and if we were doing further iterations, this is something we would absolutely consider. But we're really looking to analyze like the sort of maximum heat rejection capacity we could be seeing if there weren't any like other uses for it at like the current operation time. But yes, absolutely, most of the time there would be other uses for the heat from the reactors.
This constraint was specifically given to us in a different project from a different class.
I guess to follow on to that, you had mentioned that vessel would be operating in Arctic and Antarctic environments. So that sounds like it may like reverse, from north to south. What is like did you size your heat exchange capacity for like the warmer equatorial waters?
Yeah, the question was how did we size? Correct me if I'm wrong, but the question was sort of how did we size the HVAC units? Oh, I'm sorry, heat exchangers appropriately for use in multiple climates. We looked at a sort of worst case scenario of what's the warmest seawater we would be facing for the cooling system. So we picked like the ocean temperature of a tropical climate. I don't remember what the number was off the top of my head, but we did look at the worst case scenario in terms of heat rejection.
Great, thank you.
Good questions?
Okay, nothing else. There's one or two online, we'll try and get them quickly. How will the designs control radiation with a cooling water system that is shared among a lot of systems on the ship and the reactor?
It's a good question. The reactor itself is a closed loop. So in theory, no radiation would go to the cooling water. It would stay, it's a molten salt type reactor. So in theory, all the radiation is contained solely in that aspect of it.
The cooling water is going to a localized cooling fluid within the reactor itself. So it won't be in contact with the.
Yes.
Was any weight budget specifically allocated to reactor shielding requirements?
So the question was weight considerations given to reactor shielding? The reactor we selected is sort of a self-contained unit. So we were assuming that the shielding was already built into like the reactor unit.
What specific challenges do you envision for polar operations? For example, stability, icing, and ice ingestion in way of any sea chests?
So the question is what issues might we encounter in the Antarctic operations? So for loading on the vessel, that was taken into account using Bureau Veritas's rules for ice class vessels. And for ingestion to sea chest, that can be looked at within the next loop around the design spiral, as that is more towards the detailed design end of this, as this is a concept design.
Okay, and the last question here, are the telescopes for the passengers being used stabilized if they're highly dependent on being able to hold a fixed for viewing?
Yeah, they would most likely have a local stabilizer on them. They're not high powered either.
That's it. That's all. Anything else? Okay, thank you very much.